Welcome to AP Chemistry at Honega High School. I'm Brian Brown, and today we'll be looking at some extra help for the chapter 1 to 3 test that'll be coming up. Now, every year I've been trying to look at, what resources can I do to give students who need that little bit extra a better chance to do the best they can. And this year, one of the things I'm going to look at is these little test movies, ways to look at some of the common misconceptions and problems that I've seen on previous years so you can helpfully avoid some of those errors and misconceptions. So today we're going to look at 7 quick ones. First, empirical formula from combustion analysis. It is always the most missed question on the test, always. Students just don't spend the time they really need to get the big picture and then understand how to apply the math to that big picture. So this is always the toughest one on the test. If you get that one right, that puts you well ahead of the game. Second is just empirical formulas in general. There's often some common mistakes there. Third most missed question, and this one's always frustrating because it's such a basic idea, it's just some understanding of similarities and differences between the different types of matter, elements, compounds, and mixtures. We're also going to look at limiting reactant stoichiometry. That's a heavily missed math idea. Number 5, I say that you got to be able to count to 10 in organics and understand how to name some simple alkanes, and then people just don't take the time to do it. Ton of people miss questions. Number 6, another one like number 3, it's kind of frustrating because basic SI units. You've been talking about these for years in school, and then their derived counterparts. People miss those fundamental things. It's not that they're hard, but you don't take the time to think them through. And often it just seems like such a quick, easy question. You go with the gut answer, and sometimes that's not the answer when you really think about it. And then finally, distinguishing between molecules and ionic compounds. This is another one that just really frustrates me because this is such a basic idea. We did this so much in pre-AP chemistry. I'm not even going to tell you how to do it. I just want to remind you on a test, if I give you some substance and say which one's a molecule, you should be able to do that. If I give you some substance, say which one is most likely ionic, you should be able to do that. So that's one you need to make sure that you look at because it's always one that is a heavily missed idea. So those are the things we're going to look at today. Now, first, empirical formula from combustion analysis data. Now, this, like I said, it's always the hardest question every year because you got to understand the big picture and then you have to be able to apply it. Now, page 97 is where it discovers combustion or discusses combustion analysis. You need to read through that page if you're at all confused about this. You need to see it and see it and see it until you understand, okay, now I get what it's really talking about. And sample exercise 3.15 on page 97 takes you through that idea. Now, along the road, once we get to a certain point, really all we're doing at that point is a normal empirical formula problem. And this is discussed back on page 95, and take a look at sample exercise 3.13 if you're having trouble. So once we get to a certain point, it's just like any empirical formula problem. So we'll look at that idea at that point. So here's the problem we're going to look at. Capriatic acid, which is responsible for the bad odor of dirty socks. So if your feet stink, it's capriatic acid. It's composed of a compound of carbon, hydrogen, and oxygen. So it is a hydrocarbon with oxygen on it. Now, combustion of any hydrocarbon sample through complete combustion is always going to give you CO2 and H2O. Now, if there's other substances on it, there may be other things that are coming out, but every single atom of carbon in our original sample, and remember, we have a compound of carbon, hydrogen, and oxygen. We just don't know what these things are. But every single one of these atoms of carbon that was in this original sample is going to be in our carbon dioxide. So we can use the mass of the carbon dioxide that gets collected through combustion to determine the original sample mass of the carbon. The same thing is true with hydrogen in water. Every atom of hydrogen that is in the water vapor that comes off this combustion reaction started out as hydrogen atoms. So we can use the amount of water to figure out how many hydrogen atom or what the mass of the hydrogen atoms were. So fundamentally, you need to understand there is a connection between these two things. The carbon that is in that sample comes from the CO2, and the water that is in that sample is related to how much hydrogen we have. So all the hydrogen became water, all the carbon became CO2. Now, since when you burn something, you have to add oxygen from air, we can't use the O's in the water and the CO to determine oxygen. So big picture, you need to understand, if we can find the C and the H, so we're going to use our math to find how much C and H we have, if we can get these two things, remember, this plus that plus the oxygen, those three things added together have to equal the mass of our original sample, which is right here. So what we're going to do is we're going to find this, we're going to find that, and when I add these two together and subtract from the mass of the sample, I can determine the mass of the oxygen. At that point, it's going to be just a regular old empirical formula problem because now I know the mass of the carbon, the hydrogen, and the oxygen. So you do one type of math to get the C and the H, and you do a subtraction to get the third element, which is typically oxygen. So how do we go about attacking this problem? Well, first let's look at how much carbon we have. We know that we had 0.512 grams of CO2. Now, the book shows how to do this in a slightly different method than I use. There's some strengths to their method, but my method is just a lot quicker and takes a little bit less work. So typically, I like to use this method. If I know how many grams of CO2 I've got, I can set up a quick relationship to figure out I don't need that much space. And I know I'm going to run out a little bit, so let's shorten that up a little bit. I know I can quickly and easily find the mass of the carbon from that mass of CO2. And what you need to understand is the relationship that the formula CO2 implies. Now, we don't want grams of carbon dioxide because that's on top, and we want grams of carbon, so we have to cancel it. So that means we need the mass of the carbon dioxide on the bottom. And there is a relationship, if you have a 1 mole sample of carbon dioxide, between how many grams of carbon and how many grams of oxygen you have. So the simplest way to do this is to use that relationship. So rather than do it multi-steps, we can go straight to the mass of the carbon that we're going to end up using in the problem using this relationship. Now, if I add up the molar mass of carbon dioxide, 1 carbon plus 2 O's is 44.0 grams. If I look on the periodic table and look at carbon, that's 12.0 grams. So I know this is my mathematical relationship to solve for how many grams of carbon. And when I plug those things in my calculator, and you should be doing this, if you're having trouble with this, pause the tape from time to time and make sure you understand where and how I get these numbers. So if I go through and do the multiplication dividing, I get 0.01396 grams of carbon. Now, since I'm going to do multiple calculations here, I'm not really worried about sig figs, but yes, if you wanted, you could round it to 0.140, but you're probably going to get numbers that make more sense if you keep some extra significant digits here. So fundamentally, that's how much carbon I've got. If I do the same thing with the water, remember I have 0.209 grams of H2O. I can use the same mathematical relationship to go from the grams of water to the grams of hydrogen in the water. If I have a 1 mole sample, I know I've got 18.0 grams of water. And since it's H2, I know I have 2.0 grams of hydrogen. And this will allow me to convert from one to the other. And I end up here with 0.0232 grams of hydrogen. So that's how much carbon I had in my original sample, and that's how much hydrogen I have. So while they don't tell me those things, I can use the given information here, how much CO2 and how much water I've got to find those things. So if I want an empirical formula, you have to get mass, you have to change the moles, you have to change the whole numbers. Well, it starts by getting the mass, and that's what I'm doing here at the beginning. Now, remember the relationship. The total sample, which weighed this, has to equal the carbon plus the hydrogen plus whatever the oxygen is. And if we want to find the grams of oxygen, we know these three things are going to add up to this. So A plus B plus C, grams of carbon plus grams of hydrogen plus grams of water, I know has to equal 0.225 grams. So I can add these two together and then subtract them from 0.225, and I can determine what my grams of oxygen is going to be. So when I go through and do that calculation, as it turns out, I end up with 0.0622 grams of O. So 0.0622 6,222 grams of oxygen. Let's get rid of one of those twos there. Grams of oxygen is how many oxygens I have. So now I have the mass of the carbon, the mass of the hydrogen, and the mass of the oxygen. Now I'm ready to determine the empirical formula. Remember, formulas are not ratios of masses, they're ratios of moles. So my next step is to convert my grams of carbon to moles of carbon. So if I want to get rid of grams of carbon and find out how many moles of C I've got, it's a molar mass conversion, just like you've always done. So I want grams of C to moles of C, and for every 1 mole of C, I have 12.0 grams. Notice we're kind of undoing what we did here, and that's why the book's method's a little bit different than mine. Here, I think it's easier to establish your mass, and then it's just a plain old empirical formula from there on out. When you divide those out, you get 0.01163 moles. So that's how much carbon we've got. Now we do the same thing with the hydrogen. I want to find out how many moles of H I have so I can get the empirical formula. And I know if I have, don't want grams of H, and I want moles of H, for every 1 mole, I have 1.0 gram of H. And when I multiply and divide this all out, big surprise, exact same thing, 0.0232 moles of hydrogen. And then I do the same thing for my oxygen. Oxygen, there's 16.0 grams of O for every 1 mole of O. And you can calculate that you have 0.00389 moles of O. Now, a formula is a ratio of moles, but these mole amounts are not whole numbers, and I have to have the smallest whole number ratio of moles. So get grams, then you get moles, and now from here on, once I get this, this is like every single empirical formula problem you do. If you know the mass of the substances, and remember, if they give you the percent by mass, just erase the percent sign and put a G and do exactly what I'm doing here. So once we get to this point right here, the rest of this problem is just like any empirical formula problem ever is. So what I have to do is get grams, got it, get moles, got it, and then I need to get whole numbers. And the easiest way to do that is divide all three of these values by the smallest. Now 0.00389 is my smallest mole amount here. So I'm going to divide all three by that amount and see what I get. Now, at this point, it would be nice if everything was whole numbers or approximate whole numbers and I'd be done. Well, it turns out that when you do the calculations, that's approximately 3 and that's approximately 6. So it's almost exactly 3, almost exactly 6. And of course, that's going to equal 1. So at this point, I do have whole numbers. So I've maintained the ratio. The ratio of 3 to 6 to 1 is the same as 0.01163 to 0.0232 to 0.00389. And now I have whole numbers. So my final answer here for the empirical formula, I've got 3 carbons for every 6 hydrogens for every 1 oxygen. So that's how you tackle combustion analysis empirical formula problems as well as regular empirical formula problems. Remember, they're done the exact same way. Next, understanding the similarities and differences between different types of elements. It's such a basic question, and I think people just don't look closely enough at it in the test, and they end up answering incorrectly. What it fundamentally comes down to is this flow chart that's in the book on, I think it's page 8 or 9. Um, it takes you through exactly what you need to know to understand this idea. So pretty much any question I ask you related to the similarities and differences between these, you can answer if you really understand this flow chart. So make sure you take a closer look at that. If you have to, go back and read pages 6 to 8 over those. Next thing, limited reactant stoichiometry. This is the other thing that's going to take a little bit of time. So this is the other type of math problem that people have. This is on page 102 to 105, and sample exercise 3.18 discusses this. Now, one of the things that bothers me a little bit about this textbook is I think they kind of assume you've done this before, so they really deal with this from a very simplistic level. And in other sample problems, they get into the more challenging mass to mass type situations. But they really introduce it from a very simplistic mole to mole, and it gives you the big picture. But I think if it's been a while since you've had pre-AP and done this, it might not give you the preparation you need. So to make sure we go through and take a look at this a little bit more closely. Now here's a sample problem. Now, if you recall our discussions from class, one of the things I said is whenever you see a balanced equation in a problem, that should be a trigger. Okay, this is going to be stoichiometry. I'm going to be moving from one substance to another substance. That's the mole ratio that comes from the balanced equation. So the first thing I see here is it's probably going to have something to do with stoichiometry. Second thing I see is notice it says you have 2.00 grams of zinc and it says you have 2.50 grams of silver nitrate. When you see you have the masses of both reactants, another trigger should kick in here, and you got to know this is a limiting reactant problem. You can't just take one of these masses and figure out what's going on because one of these two numbers is actually a meaningless number. When we do stoichiometry, we're pretending if we use up all of this, if we make all of this, how much did we need or how much did we make? Well, one of these two numbers is a meaningless number. We either don't use up all the zinc or we don't use up all the silver nitrate. And just from the numbers, you can't tell which it is. So you have to have a plan of attack to do this. And I want to show you both ways. Now, the first method is easier conceptually, but it sometimes takes a little extra math. The second way is harder conceptually to understand, but it's a faster way to do the problem. And depending on what they're asking you to do, either method in the end may end up a quicker way to do it. So I want to look at this from both angles because they don't really do enough of this within the book. And if you don't remember it, you need the extra help. Now, the concept that I talked about in class is remember, the limiting reactant is the substance that gets consumed first, and when it's gone, you stop making anything else. At that point, the reaction dies. So what you're going to be doing in a limiting reactant problem is really figuring out which substance it gets used up first. And when it gets used up, the reaction stops. So you stop making your other reactant up. You stop making all of your products from that point on. So the limiting reactant is what controls everything. So you have to know, is zinc or silver nitrate the limiting reactant here? In order to answer any question about anything related to this reaction, I've got to know which one's the limiting reactant. Now, conceptually, the easier way to do this is to remember that the limiting is going to make less. Remember, when it gets used up, it's going to stop making a product. And if you predict how much, and I'm going to pick an easy one here because zinc nitrate's a harder empirical molecular formula, I'm going to pick silver to talk about this. If I predict how much silver this amount of zinc would make, and if I predict how much silver this amount of silver nitrate would make, I can compare apples to apples. Which one made less silver? The one that makes less silver is going to be your limiting reactant. And conceptually, that's the very easiest way to do this. So I've got 2.00 grams of zinc. And what I really want to do is get to silver because that's going to be an easier substance. Now, I don't want grams of zinc, obviously, because I want to get to silver eventually here. Now, there's two ways you can do this, and I'm going to end up showing you in the course of this both ways. So let's look at it big picture. It'd be nice if we knew the mass of silver. If they were asking us how much silver we could make, let's just go to grams of silver so we can figure that out. So I don't want grams of zinc. What I want to do is I want to get to silver. Well, I can't get from grams of zinc directly to grams of silver. I don't have a relationship that helps me do that. But I can get from grams to moles of zinc using the molar mass. And this is a really, really, really critical idea that you need to get here. Every stoichiometry problem, you're going from one substance to another substance. So this step we're looking at here is in every single stoichiometry problem. It is common to anything related to stoichiometry. You're going from one thing to another. You're always going to do that. What you need to understand, it's a mole to mole relationship, and that's where the balanced equation comes in. So to do any stoichiometry problem, we need a balanced equation because it gives us the relationship between things. From the balanced equation, I have 1 mole of zinc for every 2 moles of silver. Now, if I wanted to get to grams of silver, I could keep going at this point because for every 1 mole of silver, then I would have, if you look up silver's molar mass, which is 107.9, you have that many grams of silver. And then I would predict how many grams of silver I've got. Now, to technically just find the limiting reactant, I don't really have to do this step. So I'm going to make this a little bit easier, and I'm actually going to stop when we get right to here. If I want to find the limiting reactant, the limiting makes less. It doesn't really matter whether I'm talking about moles or grams. So I'm going to stop this problem right here and just do a quick two-step dimensional analysis problem. to calculate how much we get. And as it turns out, you get 0.0306 moles of silver. Now, that's not useful at this point. It could be a meaningless number. I have to turn around and do the exact same thing for the silver nitrate because I've got to predict how much silver nitrate would make. Now to keep it simple, I'm going to do the same thing. Another two-step problem. So I'm going to keep it a two-step problem, but it has to be an apples to apples comparison. I've got to go to the same thing. I'm going to silver in this case. So if you add up the molar mass of silver nitrate, it's 169.9. So that's how many grams of AgNO3 I have. And that's for every 1 mole of AgNO3. And remember, the reason I'm getting to moles is to get from moles of one thing, like AgNO3, to another thing like silver, it has to be a mole-to-mole relationship. So once again, I go to the back to the balanced equation. I've got a 2 here for silver, so 2 goes on top. And I've got a 2 here for AgNO3, so a 2 goes here on the bottom. So when I'm doing this calculation for converting the grams of zinc to moles of silver, I have to go through and do the exact same thing, plug the numbers in my calculator. And, oops, I forgot to actually write in, just noticed that. That number was 65.4. That was the grams of zinc, and that was per 1 mole. So I turn on my calculator here, plug it in, 2.5 divided by 169.9 times 2 divided by 2. I'm just going to ignore those. I end up with 0.0147. So in this particular case, which substance made less? Well, based upon these numbers, if I'm going from silver nitrate to silver and I'm going from zinc to silver, based upon these numbers, this made less. So my limiting reactant is going to be silver nitrate. So right away, at this point, I know the silver nitrate made less. That's my limiting reactant. Now, this is the easiest conceptual way to do it. Go to a common product, limiting makes less. So the one that makes less is your limiting reactant. And now at this point, every single thing I do has to start with this number because honestly, the 2.0 grams of zinc is a meaningless number. I don't use it all up. I don't have enough silver nitrate to react with all of that zinc. So when this reaction occurs, I should have some zinc sitting still in the bottom of the container. So limiting reactant then would be silver nitrate, and from there I can do the other types of math. If I went from silver nitrate to grams of silver, it would tell me how much silver I made. If I went from 2.50 grams of silver nitrate to grams of zinc nitrate, it'd tell me how much zinc nitrate I made. And the important thing to remember for excess reactant problems, which is probably the trickiest type of limiting reactant for most people, the silver nitrate controls how much zinc I use. If the silver nitrate is a limiting reactant, when the silver nitrate is gone, the reaction is going to stop. So if I want to figure out how much zinc is left over, I start with 2.50 grams of silver nitrate and go to grams of zinc. And that will tell me how many grams of zinc I used. And it better be less than 2 because I had 2. And if my limiting reactant was a silver nitrate, that means I have to have extra zinc. So at that point, you would subtract. So that's actually conceptually the easiest way to look at limiting reactants. Limiting makes less. Pick a product, change both of the reactants to that product, and see which one makes less. Now, this may be a little bit more conceptually confusing at the beginning, but in many situations, it's actually faster. So some people prefer to do limiting reactants not with the limiting make less idea, but they actually pick one of these two and go from one to the other. Like in this particular case, let me start with zinc. So let's see what this would look like if I picked zinc. So if I have 2.00 grams of zinc, I want to convert grams of zinc into grams of silver nitrate because what I want to find out is exactly how much silver nitrate would I need to use up all that zinc. And that's going to tell me which one's my limiting reactant. So it's not a limiting makes less idea here. It's a slightly more complex idea, and we'll look at it when we get a number. So I'm going from grams of zinc to grams of silver nitrate. So my first job to get from one substance to another, and that's going to always be here in the middle. That's my mole to mole step. In this case, I'm going from moles of silver to moles of silver nitrate. So that's going to be in that middle step. And at the beginning, then I need to change grams of zinc into, oops, I wrote that up there wrong, moles of zinc, because that's what I'm starting with, and moles of silver nitrate, because that's what I want to get to. So I'm going to start with the molar mass of zinc and use that to change grams of zinc into moles of zinc. Now, molar mass by definition is the mass of 1 mole. And if you look up in the periodic zinc table, zinc is 65.4 grams. Now, I'm going all the way to the mass of silver nitrate. So I've now changed grams into moles. My next step would be to change moles of zinc into moles of silver nitrate, balanced equation. 1 mole of zinc for every 2 moles of silver, but I'm not going to silver. I'm going to remember my other reactant, silver nitrate here. So it is a 1:2 ratio. And then my last step, I don't want moles of silver nitrate. I really want grams of silver nitrate, and that would involve the molar mass. Once again, it's the mass of 1 mole. And silver nitrate's 169.9 grams of AgNO3. When you plug it into your calculator, you end up getting 10.4 grams of AgNO3. Now, at this point, you have to stop and think. This is a different conceptual idea than when we looked at the whole limiting makes less of a certain product. What we're doing is we're saying, if I want to use up all 2.00 grams of zinc, I need to have 10.4 grams of silver nitrate. Do I have that? No. I've only got 2.50 grams. So that's the conceptual way you have to think of this. To use up all of this zinc, then I would need that much silver nitrate, and I only have 2.50 grams. So using this method in one math problem, we now know that the limiting reactant is the silver nitrate. Get the same answer both ways because you're doing the same thing, but it's a different approach to it. Now, why this might be more useful and quicker? Well, one, the other way, you're always doing two math problems. You're going to go from one substance to one of the products, and then the other reactant to the product. That's going to take two math problems. In this way, we can do it in one math problem. The other thing it does for you is if you're doing a excess reactant problem, if I had guessed right and I had started with the limiting reactant, which in this case I didn't because the limiting reactant turned out to be zinc nitrate, you would actually be predicting how much zinc would be consumed. And then you could subtract that from the 2.00 and you would find out how much zinc is left. So we would have to do an extra math problem. We'd have to go from our 2.50 grams of silver nitrate to the grams of zinc, honestly, if we wanted to find out how much zinc was used and therefore how much zinc was left over. So we'd have to turn around and do an extra math problem here. Well, if we'd guessed right and picked the right substance to go from one to the other, at this point I'd already know how much zinc was used, and I'd do a quick subtraction and I'd be done. So that is the limiting reactant information. And that's probably the second most difficult math thing behind empirical formula stuff for people on the test. Next one, and this is one that I've mentioned several times. You need to be able to count to 10 in organics. And it's something that is similar to what you've done before, but a little bit different. If you look at these, this is the prefixes used for naming binary molecular compounds between nonmetals. Basically, we use this for naming molecules. So you've seen this before, you've practiced it, you did it last year. Most people think this is easy. If you're naming organic molecules, and in particular alkanes, simple organic molecules of carbon and hydrogen, this is still the same, except we're getting rid of the first four here and replacing it with this. So when we go to organic molecule naming, it's meth, eth, prop, but. And then the rest is the same as it's always been, pentax, hepta, octa, and so on. So remember, it's really the beginning that's new. If you know those, you'll be able to answer some questions on the test. And that finishes off my review over ideas, hopefully helping improve your grade on the test and making the test significantly easier for you. So good luck next week.